Hi, I'm Becker Gerritsen, and my presentation is on many-valued logic circuits using carbon nanotube transistors. Now, I wanted a topic involving electrical engineering, and while looking through sample papers, I saw a bunch of similar terms that we've discussed in class. I thought it'd be easier to explain that way, because it included those. Also, there are plenty of supporting resources for me to refer to, so it's easier for me to understand. And when I finally chose a paper, it had interesting results and applications that I kind of like to share with you guys. A big part of this research is that it takes a step away from silicon and binary, which are like long-standing in electrical manufacturing. And researchers heavily argue that with more research into CNT and MVL every year, it's more and more feasible to have higher operation of computers accessed through a higher level of logic than just binary. Now, what is many value logic? Binary is two valued logic because there's two output values. You got 0 and 1, which is false and true. And then for MVL, there's more than two output values. They use ternary for this one, and for this paper, meaning 0, 1, and 2, whereas 2 is now true, and 1 it can be maybe or unknown or something else depending on what you're doing. This is deferred at an electrical level. It's all nanoscale in these circuits, and binary is found where 0 is your ground level and 1 is your supply voltage. While in ternary, 0 is still your ground, 2 is now your supply voltage, and 1 is half your supply voltage. Also meaning that you have to read at half the potential differences for ternary, which is much harder, but can be worth it. Because having more than two values can allow for more information transmitted per wire, or more storage per cell, and all this leads to like a more storage dense solution, allowing for less power dispersion, allowing for like a better computational speed. It is at the expense of having to read through more noise and also like more transistors because like the more complex circuit can take way more transistors. But for this case, they managed to negate that number and cut the number of transistors in a circuit. Now, why they use CNT transistors? The semiconducting properties of CNTs, you guys have all read about them. By doping them or changing the conditions of the semiconductor, in this case, changing the chirality or diameter of the carbon nanotubes, they're able to cover the full range of the P and N dope regimes, which just means they're able to become as insulating or conducting as needed for this purpose. Now, the tensile strength of CNTs are also like pretty astounding, which is another reason why they're used in a lot of other consumer products. And also, silicon is just pretty bulky, and it's not ideal for a storage dense solution needed for MVL. Logic circuits, you've probably seen gates like these on the top left, not or an and, especially if you've taken a discrete math class, but those are each gates, and combinations of those gates are used to make logic circuits. Each of these gates are made of transistors, normally made of silicon, which are all made through photolithography typically. You probably remember that as the top-down approach to creating nanostructures, using light to create a pattern on a substrate. Carbon nanotubes in transistors are typically made through laser ablation or CVD, but these logic circuits are supposed to be better for binary when they're simple, like just using a not and or gate, kind of like on the left. But on the right, that's a 2-bit comparator, and that's a way more complex circuit where MVL can thrive for a reason we'll get into. So although X is less than Y, X is greater than Y, and X is equal to Y for 2-bit comparisons, which is what the research paper decided to make, that looks like a simple operation where a binary would be ideal. They managed to work around it. Now, they did this by using negation of literals. The negation for ternary works differently than binary because binary is just a negation, 0 is 1, 1 is 0. Ternary has 3 values to go between, so that allows for different laws and different combinations of circuits when negating. And some of that's using the equations that they provided on the left. They worked through all of this and heavily explained it all, making a very quality paper. But using the negation of literals, they were able to reduce sum of products, which means less outcomes to account for while creating these comparators, and that means less gates, less transistors, in a more efficient circuit. Here, the circuits they designed, they didn't actually create them physically, but they simulated them and they did work. You have greater than on the top left, on the top right you have less than, and on the bottom is equal to. Now, the results and implications of this, you can see how many transistors they cut in each of the circuits in the table at the bottom. It's pretty impressive. They cut it by half in each of them, more than half in most of them. It all relates back to how I said higher density solution, improved operational speeds, An impressive thing that they didn't really address is the supply voltage they used. It was only 0.9 volts. And for a ternary system, that means they have to read all the way to 0.45 volts. And a zero point 0.5 volt solution is typically like considered ideal for these in using binary, which is really impressive. Now, this also has huge implications for RAM or ReRAM, RRAM. It's called a bunch of things. It's an unpopular type of RAM or storage because it just costs a lot, but it uniquely retains storage when cut from power, meaning it's non-volatile. And with it's going to be easier to make if technology such as this that's used to make it can have more research into it. Now, my outlook on this is I think it's an impressive feat using nanotechnology. It doesn't necessarily advance nanotechnology, but it uses nanotechnology to advance another area of science, and I really appreciate that. The paper is my favorite part of the paper is that it can be built off of by other researchers because it explained its work well and also like left it apart that heavily allowed for more room for innovation. That being said, it's not commercially feasible. Like CNTs are just so much more expensive than just silicon transistors. In after decades of research into CNT transistors, that just hasn't changed. Also, ternary is just such a rare system, and creating compatibility between that and binary devices can be a bit of a challenge. Or finding other people that know how to create ternary systems. So if I did have to recommend an industry where this is used for, I'd say maybe like an industrial setting or an academic setting where money might not be so much of an issue, but computational power is needed. Here are some of my references, and thank you. Have a great summer.